And
So
the potential is controlled by what? Like the thickness of the nanowire or the material? Or?
It's actually a pulse that's built in, that's basically applied through this atomic force microscope tip.
Oh, I
and
see.
which gets built into the.
I see.
So there's
So
actually
what, the atomic
a paper.
force microscope goes across and writes a pulse to the nanowire.
Right.
And that stays there. After that. Okay.
Right. Okay, so to summarize, we've seen that we can use spins and their interactions in order to construct designer quantum materials. And we've described a mechanism for producing topologically stable flying spin qubits and generating EPR pairs within a solid-state system. We've talked about how domain wall qubits with tunable exchange interactions can be used to construct quantum spin systems. We've shown how spin-orbit superlattice quantum wires can spatially map out electron spin resonance, and how we can encode spin manipulation into the band structure of the superlattice. And we've mentioned some possible physical implementations of these spin-orbit superlattice, of these designer quantum materials. And so there are many possible future directions that we could explore, and I'll just mention a few of them briefly here. So first of all, we might be able to build on the fact that new resources emerge in these designer quantum materials that don't exist for the individual building blocks. So, for example, we've seen that using only antiferromagnetically exchange interactions between individual spins, we can generate effective ferromagnetic exchange between logical qubits, which act as effective spins. And so this means that we can investigate, for example, electrically switching between ferromagnetic and antiferromagnetic materials within the same system. We've also seen that we can explicitly incorporate topological features such as domain walls into exchange-coupled spin systems. And so we could extend this idea by introducing analogous domain walls into systems with spin-orbit coupling. Or alternatively, we could study the topological features which emerge as a result of constructing these designer quantum materials, but which didn't exist in the beginning. So another possible direction we could take involves extending the scope of spatial analogs of quantum dynamics. And we might do this by, for example, constructing designer quantum materials using both exchange and spin-orbit interactions. And this might enable us to generalize this single spin qubit spatially encoded gates to 2-qubit gates, and perhaps even encode quantum algorithms into the band structure of the superlattice. And finally, we could also explore how it might be possible to combine the different classes of designer quantum materials that give rise to flying spin qubits, EPR pairs, spatially encoded quantum gates, and new elements in order to construct a full quantum architecture for quantum information processing that satisfies all 7 of the DiVincenzo criteria. So finally, there are many people who have made this work possible, and I wish I could thank all of them here, but that's not possible. So I'd first of all like to start out by saying that I don't think there's any possible way I can do justice to thanking my advisor, Jeremy, for all of the guidance, opportunities, and foundation that I've received over the past few years. I'd also like to thank our theory collaborator, Dr. Hellberg, at the Naval Research Lab, for all of his help and support, and without whom a lot of this work wouldn't have been possible. I'd like to acknowledge very helpful discussions I've had with several individuals, Jake Taylor, Florian Meyer, Yakov Weinstein, and many others, that have helped my understanding of this material a great deal. I'd especially like to thank my thesis committee, Dr. Waldeck, Dr. Griffiths, Dr. Dutt, and Dr. Swanson, for all of their valuable advice during the course of my research work. I'd like to give a special thank you to Dr. Singh for all of her inspiration since way before I even knew what research meant, and for all of her inspiration in inspiring me to start all this work in the first place, and for all the inspiration and support she's given me ever since then. I'd like to thank my thesis committee, Dr. Singh, and many other professors I've had, and I've been very fortunate to receive a foundation from as an undergraduate and graduate student at Pitt. I'm very grateful to many friends, both within our research group and outside the group, for all of their help and support, and also the department office staff for their help, And finally, my parents and my younger sister, Savita, for a lifetime of support. So finally, I'd like to acknowledge these funding sources and thank you all very much for your attention.
Questions?
Yes.
What are in these flying qubits, what are believed to be the main sources of decoherence?
So the decoherence processes we believe that are most important are those that are also for spin cluster qubits, which are basically nuclear spins if you're talking about 3-5 materials, or coupling to inhomogeneous magnetic fields, fluctuating fields. And so those processes actually affect the system in different ways for spin cluster qubits. For example, if you have an inhomogeneous magnetic field, because you're looking at the total spin of the system, that doesn't scale with the number of spins in the qubit. But on the other hand, if you're looking at nuclear, I should say that the other way around. So the nuclear spins, that doesn't scale with the number of spins in the qubit, but the fluctuating magnetic fields, because they act individually on the different systems, that will scale with how many spins that you have in the system.
Does spin-orbit coupling come in, because that's going to be present in the real materials?
So actually that's an interesting point. So spin-orbit coupling, definitely if you're moving electrons through these materials like silicon and germanium quantum dots that we're envisioning, will play a role. But actually the mechanism that we're looking at is basically one for moving the spin information without moving the individual electrons. And so we think that that actually limits the effects of spin-orbit coupling that you would even have in this mechanism.
But you have to move the electrons inside the dots in order to change the coupling,
sure.
right? So,
yeah, sure. So yeah,
is there a significant spin-orbit effect there, or some other decoherence mechanism?
The effect, I guess, would be to produce, for instance, anisotropic exchange coupling between spins. That would change the symmetry of the interaction and everything.
This EPR pairs that you were talking about, is there any chance that you could actually measure those various parts of the EPR pair, or are they like somehow bound and inaccessible? So then,
you could measure individual qubits, for instance.
no, but what you care about is that
The correlation.
in those pairs, yeah.
Yeah.
Right. Can you?
I guess what you could do is you could.
The pairs there were between two domain walls, or
Right.
Yeah. Right.
Right.
Exactly. So
Right.
what you really care about is sort of.
Yeah, so you could basically, we have this method of localizing and delocalizing these single qubits. So if you could localize, for instance, the EPR pair, basically the domain wall, which represents this single spin qubit, if you could localize the two spins associated with them, then you could probably measure them the way you would measure a single spin EPR pair.
Well, how would you measure the spin in these cases, right? So you have it associated with your domain wall, and it's come to the end of the journey, and
Right.
what do you actually do with it?
Right, so you could measure the state of the spin the way you would measure, for instance, a spin cluster qubit, which is basically by measuring the individual spins in the cluster, and that actually determines the spin density, which determines which state which spin cluster qubit you have.
Isn't that rather impractical for these little things sitting on quantum dots? How would I get the Z component of spin of an electron sitting on a quantum dot? That's what you're looking for.
Right, so, if you're asking about measurement methods, or...
Is there any?
There are methods for measuring single spin qubits. And so those methods involve, for instance, spin-dependent tunneling out of a single dot, and or conversion to optical information, the polarization of emitted light. And so we envision that, if since we have this mechanism to convert between localized and delocalized qubits, one possibility is to convert the delocalized qubit to a localized qubit and then measure it using single spin techniques.
And you think you can do that successfully for each pair of the EPR part? Because that's what you need to do to
Right,
measure
so that's what I was trying to
Right.
say.
Okay.
Just that we leave it to the experimental.
Right.
Well,
I mean, there's only,
But that would be the idea.
yeah.
Well, they
so,
should.
yeah, that's
So you could let those 2 electrons tunnel into a superconductor. Well, no, I mean, it's
Sure.
not crazy.
Well, one
They're in
other
a singlet state, then they'll just form a Cooper pair. There'll be no barrier.
Is there any way to like also look at like this topological part of this protection? Like, I mean, would you say that there was some way to measure the topological index somehow of
of the state.
Yeah, of the state.
Well, I mean, one of the quantum, the quantum number, this neutral spin 1/2 state, has this spin charge separation. That's one of the topological features of this state. So, I mean, measuring the spin would be, like measuring a topological feature. But in terms of maybe
But how
things
do you
like
know
Berry
that?
phases or something
that's
else.
what I was wondering. Yeah.
I'm not really sure like how you would measure that.
Okay. No.
Well, maybe we can excuse the non-committee members at this point. Thank them for
Thanks.
coming. You can take that camera.